Okay, so what we're going to look at real quickly is friction and how to handle friction. So some of the forces that we've learned about, tension, normal force, are examples of forces that don't really have a set formula to calculate them. They're just a name that we give certain forces. Normal force is the force by a surface. Tension is the force by a rope or a chain or something. Other forces have like their own separate way of calculating them. For example, you already know weight has a formula. Weight would be mg. Friction is one of those forces that has a little formula that goes with it. And like in our lab demonstration the other day, it turns out that friction depends on just two things. Some things it does not depend on are surface area, speed. They don't make a difference. Turns out the only thing that makes a difference is the normal force that the object is experiencing. In other words, a lot of times that's the same as the weight. For a typical horizontal motion type thing, it would be just the weight. But if another force is pushing down on it, or if it's at an angle, or there's a lot of different circumstances where it may not be exactly equal to the weight. What's important is the contact force, or the normal force. We'll look at some examples later on of where the normal force gets affected. It's not exactly the same as the weight. But friction is affected by the normal force. I'll put force in there. And we'll usually use a capital N for that. Sometimes you'll see F sub N. And the only other thing that matters is the types of surfaces involved. Now, that is called the coefficient. The number that we use is the coefficient of friction. And there are an infinite number of these coefficients of friction. They are just numbers that describe how sticky two substances are in relation to each other. So there is a number out there somewhere in some book of tables or something like that. There's some in your textbook. You look them up. For like rubber on concrete, which would be your typical tire, right? Or, I can't remember, sandpaper on wood, or all kinds of different possibilities. And there'll be a list of them in your textbook. And a lot of times they'll be given in a problem. So, how are they affected? Well, the bigger the coefficient, the more friction there is. The bigger the normal force, the more the surfaces are pressed together, the bigger friction is. So the general idea for friction is that the force of friction is just the product of the coefficient of friction, which is mu. Goofy little letter, looks like a U or an M, it's Greek, it's mu, times the normal force. The fun doesn't stop there, though, because friction comes in two varieties. You see, when an object is stationary, the atoms in the molecules down at that atomic and molecular level get a chance to grip each other a little better. So the friction for stationary objects tends to be a little larger. They call that static friction. So the force of static friction is the coefficient of static friction times the normal force. So in other words, there's any pair of substances, there's really two coefficients, one for static situations, and the force of kinetic friction, when something's moving, kinetic meaning moving, like kinematics, right, is the coefficient of kinetic friction times the normal force. So the general form doesn't change, it's just we use a different coefficient. So we may use static friction up until the point when an object starts to move. So the force of friction, static friction that is what you need to overcome to get something to start. If you pull on something with 3 newtons, the force of static friction will pull back with 3 newtons if it can. If you pull a little harder at 10 newtons, the force of static friction will pull back at 10 newtons if it can. But at some point, the static friction can't hold out. So let's say you pull with 17 newtons. That's just enough force to break static friction and move the object. So this formula here is really the maximum force of static friction. That's the force you'll need to pull to overcome in order to get something to start moving from rest. Once it starts moving, well then you got to go to this. Got to go to a new coefficient and a new equation or a new number for friction. Generally, kinetic friction is less than static. So the coefficient for kinetic friction is generally a smaller number than the coefficient for static friction. So, knowing that this is how we might calculate friction, this gives us another level to look at. Let's look at a relatively simple problem. Let's jump to number 12. So number 12 in your packet looks like this. It says a 47.8 kilogram crate rests on a level floor at a shipping dock. The coefficients of static and kinetic friction are 0.747, notice no units, and 0.324. Notice that they're different sizes, the smaller one being kinetic. What horizontal pushing force is required to A, just start the crate from moving? Well, that tells me that we want the point at which static friction is broken. So for example, for part A, I don't really need an elaborate free body diagram, but the fact that it says level floor says that the weight of the object, in this case, is the same as the normal force. Now, that's often the case, but doesn't have to be the case. And they want our applied force to be just large enough to start it in motion. So basically, the last possible moment of equilibrium. In other words, we are looking for this force of static friction. So our goal is really, ultimately, just to find the force of static friction. And in this case, we got enough to do it, because we can tell just by the situation that in the y dimension, that in the y dimension, the net force is 0. It's equal to the normal force minus mg. And that the net force, of course, is equal to mass times acceleration, but it's 0, because it's not accelerating in the y at all. So 0 equals normal minus mg, and that means that the weight is equal to the normal force. The positive version of the weight is equal to the normal force. So if I know the weight, I'll know the normal force. Well, we got that because they give us m. They tell us the mass is 47.8, so we have enough to find the normal force. So mg is going to be 47.8 kilograms times 9.8, and we'll get that weight, which is going to be equal to the normal force. So our normal force will turn out to be, magic calculator, okay, normal force is going to turn out to be 47.8 times 9.8 equals. So I'm going to get a normal force of 468.4 newtons. So, going back to what we said earlier, I'm looking for in part A the force just required to start it moving. So I'm looking for the force of static friction. But static friction can be found by taking mu static times the normal force, which I've just found. So this force of static friction, which my applied force has to overcome, is going to be found by taking 0.747. That is the mu of static friction for this material, for this combination of materials, wooden crate on dock floor. Times the normal force, which is the 468.4 newtons. And the force of static friction will be, and therefore the force I need to overcome, will be okay, hold on, boom, 0.747 times 468.4. So the force that I will need to push with to overcome to get it to just start moving is about 340 49.9 newtons. Just a little over that, and bam, it'll start moving. But of course, once it starts to move, I no longer have a static friction situation. I have a kinetic friction situation. So in order to slide the block across the floor at constant speed, I have to deal with kinetic. So we jump to B, and in part B, what we're looking at is this. I have my applied force, normal force, which is equal to the weight. We already know both of those. Now, how hard do I have to pull compared to friction in order to move it at constant velocity? You should pause the video, and I'm going to see if you can answer that yourself. Welcome back. So, if I'm moving it at constant velocity, that means this thing has to be in equilibrium. Acceleration is 0, net force is 0, and that would mean that my applied force is the same size as the force of kinetic friction, because now it's moving. So, once again, what I'm looking for is the force of kinetic friction. Well, straightforward, because the normal force and weight don't change in this situation, so I get force of kinetic friction is going to be mu kinetic times the normal force. So that, my force needs to be equal to the force of kinetic friction, which is going to be I need the mu, I got to go up, 0.324 times the normal force, which is 468.4. I'll leave the math up to you, but we should be okay at that point. Did I get the first one right? Let's look. Hey, I'm a freaking genius. I'm guessing the next one comes out to be 151 and some change. In a little bit, we'll look at a problem when I will do inclined planes, and at the end of inclined planes, we will look at a problem that involves both friction and inclined planes. It'll be the most exciting moment of your life. Take care. Bye.